Welcome to Spring LIB.
For this problem, you are given an herbicide with a known composition of just carbon, hydrogen, nitrogen, and chlorine. A 0.1 gram sample or 100 milligram sample of the herbicide is combusted in excess oxygen, and it produces a particular volume of carbon dioxide and a particular volume of water vapor at STP. Let's first start by calculating the moles of carbon that are in the compound as expressed in carbon dioxide and the moles of hydrogen in the compound as expressed as the amount of water vapor. So if we have 83.16 milliliters of carbon dioxide, we can convert it into liters by dividing by 1,000. Now that we have the liters of carbon dioxide at STP, we can use the conversion factor 22.4 liters in a mole at STP to calculate the moles of carbon dioxide. We simply divide by the 22.4 liters. When we know the moles of carbon dioxide, we can calculate the moles of carbon, recognizing there's 1 mole of carbon for every mole of carbon dioxide. And we get 3.71 times 10 to the negative 3 moles of carbon. We can do something similar with the volume of water vapor. We can take the milliliters of water vapor, divide it by 1,000 in order to get the liters of water vapor, and then because it's at STP, at that particular volume, we can divide by 22.4 liters to calculate the moles of water vapor that are present in the 73.3 milliliters. Then when we have the moles of water vapor, we can multiply it by 2 in order to calculate the moles of hydrogen, because there are 2 moles of hydrogen for every mole of water vapor. And we get 6.544 times 10 to the negative 3 moles of hydrogen. To calculate the moles of chlorine, we simply need to take the mass that was determined in a separate analysis of 16.44 milligrams and divide it by its molar mass. First, let's get the milligrams into grams by dividing by 1,000. Then when we know the grams, we can divide it by the molar mass to get the moles of chlorine. 4.638 times 10 to the negative 4 moles of chlorine. Before determining the empirical formula of this compound, it wants us to calculate the mass percent. So we can do that now with carbon. If we have 3.71 times 10 to the negative 3 moles of carbon, we can multiply that by the molar mass of carbon, 12.011, to get the grams of carbon in the 0.1 grams of the sample. We divide that by 0.1 and multiply it by 100 to get the percent that is carbon, 44.59% carbon. We can also do the same thing with hydrogen. Let's take the moles of hydrogen, multiply it by its molar mass to get the grams of hydrogen, and then divide it by the grams of the entire compound and multiply by 100 to get the percent that is hydrogen. And we get 6.596% hydrogen. We can do a similar calculation with chlorine. We know the mass that is chlorine. It's 16.44 milligrams or 0.01644 grams. We'll divide that by the mass of the compound and multiply it by 100 to determine the percent that is chlorine. And we get 16.44%. Now that we know the percent of everything but nitrogen, and all the percentages should add up to 100, we can calculate the percent that is nitrogen by subtracting the percents of everything else from 100, and the remaining percentage should be the percent that is nitrogen, 32.37% nitrogen. But to get the empirical formula, we need to know the moles of all of them coming from the 0.1 gram sample. Now that we know the percent that is nitrogen, and we know the mass of the sample, 0.1 grams, 100 milligrams, we can multiply the percentage by the mass, and we'll get the mass that is nitrogen. The mass of the 100 milligrams or 0.1 gram sample that is nitrogen. We can then divide that by the molar mass of nitrogen to get the moles of nitrogen in the 0.1 gram sample. 2.311 times 10 to the negative 3. Now that we know the moles of each element in the 0.1 gram sample, we can divide by the smallest mole value, which is 4.638 times 10 to the negative 4. And this will hopefully give us some whole numbers corresponding to the mole ratios of each element in the compound. This first one is 5, the next one is 8, and then 14, and this one of course is 1. So the empirical formula then is going to be 8 carbons for every 14 hydrogens, for every 5 nitrogens, for every 1 chlorine. Given the empirical formula, we could also calculate the molecular formula if we knew the molar mass of the compound. We don't know the molar mass of the compound, we just know the mass of the compound, 0.1 grams or 100 milligrams. If we knew the moles that corresponded to this mass, then we could calculate the molar mass of the compound. We'd simply take the mass, 0.1 grams, divided by the moles. Once we have the molar mass, we could then use it to determine the molecular formula. So the last piece of information that we would need really is the moles of the compound that corresponds to 100 milligrams.